Testing and
Alright guys, we're gonna get started. Welcome to week 2 of our Waterloo Robot Learning Group. I'm holding my phone because I forgot my microphone cable. So this is recording the audio. First announcement. If you took a look at our Luma page, what I tried to do is, so first of all, there's the additional reading list every week that I give you guys. But also, there's this annotation link in Alpha Chive that we can try out. And basically what this enables is, if you have questions or if you have comments, before we start our reading group every week, you can leave some comments here. You can highlight passages, and you'll be like, oh, you can make some comments. So this is going to be our way of discussing ideas or things that doesn't make sense, right? It relies on you guys reading the paper first, though, before coming. But yeah, I think every week we're going to try to have this. So for this week, I assume like not that many people saw this link, but okay, Krish has a comment here defining the method. Okay, these are notes, right? So if you have questions, you can put them here. So yeah, any logistical questions so far? And then we're also going to, I learned that this room at 7 is taken, so we'll probably have to move at 7. And in the future, I thought it was a one-time thing they're meeting, but it turns out it's like a recurring thing. So we'll figure out a new place. And also, timing-wise, is Thursday still good, or do we want to move it?
Wasn't last week it was on Wednesday, or?
Last week was also Thursday, I think.
Oh, okay.
Yeah, we can.
Thomason said he wanted to move it.
Huh? Thomason, yeah, wants to move it, but does anyone else want to move it?
I think I have a different spot in mind. Do you guys know about like the
Akatos?
Akatos? Yeah.
That's too far.
That's too far, yeah. I think it's too far for me too, yeah. I prefer it just be.
Sorry?
That'd be a 6 spot.
It's 6 spot.
I've been to the house, it's very nice, but it's just too far.
Yeah.
Like, I'm not gonna be reading 30 minutes.
It's like you take it to.
We can do it like once in a while, but I think here is like we're in the campus and it's closer.
I think like, even like if it's any like engineering building or like the STC or the MC, like that's fine, but Akatos is kind of far.
Okay. Yeah, I'm trying to get that room like on the same floor. It's like it's like a nice enclosed room. I don't know, in front of the elevators, if you know what I'm talking about. Like over there, and it's like kind of nice. And there's a podium, small podium. Huh?
Sometimes the one on the 3rd floor.
Okay. Yeah, I'll need to figure out how to book that. But anyways, so that's logistics out of the way. Today we picked the V-JEPA 2 paper. The topic for this week was the world models, right? So we asked last week what topics you guys want. So this week we picked world models, and V-JEPA is going to be the paper that we're going to be presenting. So we're going to follow a similar structure to last week. If you weren't here last week, basically we go over the paper, I'll give a presentation, and then Krish will cover the second part of V-JEPA, and then we'll have a discussion. So yeah, let's get started. So number 1, this paper that we picked out actually has it's a follow-up of many papers. So but first of all, the paper is written by Jan LeCun's group at Meta. And so LeCun talked a lot about world models for a pretty long time. So he wrote a paper, or sort of like a opinion paper, A Path Towards Autonomous Machine Intelligence, which talked about JEPA, or first introduced his idea of JEPA. And then there's the iJEPA paper that came out in 2023, which was about image-based JEPA, and then V-JEPA came out in 2024, and then now we're covering V-JEPA 2, which is a follow-up of the V-JEPA, V standing for video, and I standing for image. So I'm just going to give an overview sort of like of the architecture and sort of some motivation. So first of all, world model, what do we mean when we talk about a world model? I think very loosely, right, world model is some model of the world. So yeah, world model has been a term that's been used like quite loosely recently, right? One way to think about world model is you have an agent interacting with the environment, right? So the environment is like the physical world or some environment in sim. So if you had your own world model, instead of having to step through this physical environment, you have your own world model that you step through, right? It's like sort of your own perceived environment. That's one way to think about world models. But even more loosely, the way you can think about world models and what you'll see in JEPA, right, is just a world model is just some representation of the world, right? it's not necessarily something that you can directly interact with. So here it's like, it would be like you give a state or given a state in an action, what is the next state? But more loosely, it can just capture some like representation of the world. And so to motivate this, and what you'll see in the paper, they talk about like joint embedding architecture and generative architectures. And what is all of that about? I think one way to motivate it is through sort of like looking at the history of representation learning, right? So as I said, like a world model is really just some abstraction of the world, or you can say it captures some representation of the world, right? So like if I give you an image of a dog, right? You know that it's a dog. A dog is some abstract concept that you understand. If I show you two different images of a dog, you understand that both of them are the same thing, right? So traditionally, one way to do representation learning would be like through the supervised learning. So like if you're familiar with YOLO doing object detection, right? One way, what you would do is you train a model, it takes images and it tries to predict the class. And what you would do is, let's say you have some other task, right? You can just freeze this backbone and you just slap on a new head, right? And you would be able to predict new classes. And the idea is that this backbone should ideally capture some useful semantic representation of what these images represent, right? So this should this entire model should sort of understand what these images capture, like some deeper meaning beyond just pixels. And then you can just like learn something lightweight, attach a new head. And so that's like traditionally, and this is called transfer learning. You just transfer from one task to the other task. And this would be supervised learning. More recently, we have the idea of like self-supervised learning, right? So in supervised learning, you have these images and you have your own labels. But that can be very expensive to create your own labels. So one idea is if you can just use the structure of your data to create its own labels, right? So one idea would be you take an image, right? And again, we're trying to do representation learning. We're trying to understand meaningful representations, or learn representations of the images that could be useful for downstream tasks. So one way to do this is a lot of these are like contrastive methods. So last week actually, we talked about CLIP, right? So in CLIP, what we would do is we take these are image and text pairs, and we have an image encoder and a text encoder, right? Both of these will encode the image, and encode the text and the image in some latent space. And what we're trying to learn is that, let's say you have an image of a dog and the text that says dog, right? You're trying to teach the model that these two really mean the same thing. And so you're going to try to take the image embedding and text embedding. You're going to try to make them super close in this latent space if they represent the same thing, and you're trying to pull them apart if they're different things, right? If you're showing you an image of a dog and the text is a human, then they're not compatible, so you're going to try to push them away. So that's CLIP. Right, so this would be for image and text. You can also just do it for the same image, right? So the way you do it for the same image is, let's say I have an image of a dog, and I give you another image of the same dog. So you take the same image, but you augment it. So you can crop it, you can add like different colorations to it. So at the end of the day, it's still an image, right? If I give you an image of a dog and I just like make it black and white, or I zoom in, it's still the same image. So if you apply augmentations to this image, the model should still sort of like be this augmentation invariant. It should, at the end of the day, it should learn that these two really mean the same thing. And then on the other hand, another way to do self-supervised learning is you take an image and you mask parts of it, right? And then your goal is to reconstruct the mask the cropped images, right? So if I hide like you see the gray blocks, those are hidden, and the objective of this model is to reconstruct these hidden, or these patches that were hidden to the model, right? And so in all these cases, the world model, or the thing that learns the representation, are these encoders, right? These encoders should hopefully take your original inputs and then put into some representation. And this representation is like a good capture sort of these semantic meaning of the image. And now we're going to get back to this diagram that the paper shows. So if you look at your paper, V-JEPA, they present joint embedding architectures, generative architectures, and joint embedding predictive architectures. And so the architectures that I've shown you so far sort of fit in either of these, right? So let's take a look at how they fit. If you look at our SimClear and our clip images, where we take augmented, or this is SimClear, you take an image, you augment it, this is clip. What you're doing is you have your input X, right? So X would be like either a cropped, or sorry, it would be like an augmented image, and Y would be the same image but not augmented. You encode both of them, and your objective is to sort of like minimize their distance, right? Or like you're trying to learn that these two actually mean the same thing. So that's under the joint embedding architecture, and you can apply this to clip as well, right? So you have, let's say you can imagine text and image, and you're trying to learn that these two are really the same thing. And then you have the generative architecture, where our goal is you take your input, which is masked. So X here would be this masked image, or patches of it are masked, and then you encode it, right? And then the Z here is like extra information that can be useful. In this case, you will tell the decoder which parts of the image are actually masked. Like these are these gray patches that tell you, okay, these are actually the patches that I need to reconstruct for my target. But the objective of the decoder is to reconstruct the original image Y, right, your target Y. And so you can see how it sort of fits in this generative architecture paradigm. And then joint embedding predictive architecture, right? It's very similar to generative architecture, right? But all they're doing is adding an encoder for Y, okay? So instead, this is very important. Instead of having your decoder directly predict, right, the pixels, because if you think about it, right, what this is learning, right? So our objective is to reconstruct this image, right? So we live in pixel space, right? So our decoder will take information from the encoder and try to reconstruct the pixels. So if you think about it, what is the encoder going to learn? It's going to learn things that are going to be useful for the decoder to reconstruct the image. And the argument here is that perhaps this is pretty bad. And why it's bad is because the things that the encoder will learn, right, it's going to learn only things that are useful to reconstruct these pixels, right? And pixels can be quite noisy, right? Like there's noise that can be, there's going to be a lot of noise with pixels. It could be argued. And so what LeCun's team thinks is that instead of directly working in this pixel space, we're going to add a layer. Like we're not going to predict this. We're going to encode this in some latent space. So your Y goes to an encoder. It exists in latent space. And your objective, your reconstruction objective, will exist in the latent space, right? So you're just introducing this extra encoder. And so this is the fundamental idea behind JEPA, right? And it takes ideas. So this joint embedding predictive architecture now is no longer generative, right? Because you're no longer trying to reconstruct your original target Y, right? So there's no way, you can predict when you go to the encoder, what it's going to be, but there's no way from going to latent space to your original target Y, right? So it's not generative. An extra note, as I was trying to study on this topic, I sort of have it here, is another way to think about sort of this method. I don't fully grasp it, but what I want to say is sort of you have this collapsed contrasting methods and regularized methods. So JEPA, they argue, is like a regularized method, right? And there's this contrastive methods. Okay, so let me explain this for a quick second. So if you look at your contrast, this joint embedding architecture, right? If you think about it, you might run into a big issue where you end up with this mode collapse, right? So imagine I give you an image, right, and I give you another image, and they both go through an encoder, right? And your objective is just to make sure that if they're the same image, or sorry, if they're similar in the embedding space, right, that this distance, or this V, is minimized, right? And imagine I only give you pairs that are compatible, right? What is going to happen if I only give you pairs that are compatible? There's a trivial solution to this problem, right? The encoder could just predict a constant, right? And so it collapses down to just learning a constant, right? So in contrast to learning, right, so these are compatible pairs. So imagine X and Y, right, and these are points, and these points are compatible, but if you just show these examples, it's going to collapse down to a plane, and you just learn basically a single value, right, for all these points. It doesn't matter what point. So that's why you introduce negative examples, right? So as you introduce negative examples, right, the way you view this is sort of like, this is the D, right? This is sort of like, what is it, the actual distance between these two embeddings. So what you want the model to learn is, okay, these are incompatible pairs. So we're gonna try to maximize the energy here, because they view it through the energy-based model. Right? You're gonna try to maximize. But as you can see, it's gonna take a lot of negative examples. So that's one limitation of contrastive methods. You need to show a lot of negative examples. So everywhere where the points are not compatible, you sort of learn this landscape. And there's regularized methods where sort of like you're able to learn this landscape just from the architecture, right? And you don't have to do this hack of like, oh, you have to give you a lot of negative examples such that you get this sort of like nice landscape. I guess for me, I didn't fully internalize how JEPA sort of like enables this, well, like, why it just like does this, right? But let's go a bit more into JEPA and V-JEPA and in terms of how it works. So this is a screenshot of how V-JEPA works. This is from the first V-JEPA paper, not V-JEPA 2. V-JEPA 2. So the main difference is now we're working with videos, right? Videos are just sequences of images. And very similar to, I guess, the mask autoencoder idea, the objective is to reconstruct a video, but you're going to mask it, right? You're going to mask it, and number two, we're going to work in a latent space. So instead of directly predicting our image, we're going, or our image with the unmasked, or we remove the unmasked tokens here because when we're doing the prediction, we only predict the tokens that were masked, not like the entire image. Right? So we're removing the masked tokens. But notice here, it goes through the encoder first. So if you were just to do like masked autoencoders or predict directly in the pixel space, it would not go through the encoder, right? So you go through the encoder, remove these unmasked tokens so that your targets are only going to be the ones that were masked. And then on this side, you take your original image and then like remove all the tokens that were masked, so you only have access to the unmasked tokens. Go through the encoder, and then you introduce the ones that were masked, you introduce masked tokens, go through the predictor, and then the objective is to minimize so that this should be consistent with this. Right? And then there's a couple hacks here, or tricks, so that you don't suffer from representation collapse. I guess, yeah, let's first go over here. So this is the loss objective that they present in the paper. All right, so the notation might seem scary, but E is essentially the encoder, P is the predictor, and delta Y is, I believe, the tokens, the positions of the masking, the positions of the parts of the image that were masked. Right, so it knows, the predictor knows sort of like, okay, which were the parts of the image or the video that were masked. And so under the original formulation, without any tricks, it doesn't work, right? Because as I said, you just end up predicting a constant, right? If your encoder just predicts 0 or 1, right? Any fixed value, you sort of like have a perfect, like a 0 loss. And so what you need to do is introduce these stock gradients, and the encoder for Y is actually the same as the encoder for X. All right, so if you look back at this image, this is actually going to be a copy of this, except that the weights of this will be an exponential moving average of this. In other words, it's sort of like a slower, it's a weighted average version of the weights there. And I guess intuitively, what this amounts to is that you sort of like, because you can imagine if like both of these share the same weights, or if you don't do this, then it's very unstable, your training, right? So by doing this, by doing it as an exponential moving average, you sort of have more of a fixed target that you're going to optimize to, right? So if you look at your loss, right, this is what your network predicts. This is your target. If you always let this change all the time, it's like very unstable for your training. And the other thing is the stop gradient, so you don't let gradients flow from this part of the network. Right? Yeah, so that's our objective. And I think those are the main pieces. The masking strategy, we can briefly talk about it, like how they mask. They have short-range masks and long-range masks. And so this might be surprising to some of you, right? It ends up masking over 90% of the video, which is quite a lot. If you look at like the masked autoencoder paper, so that was when that's referring to this architecture. If you look up masked autoencoders, I think the full name of the paper is like masked autoencoders are scalable vision learners, or yeah, something like that. They also like mask a lot of the image and show that it actually improves performance when you increase the amount of the proportion of the image that you mask. Okay. So yeah, similarly for here, we have a lot of masking. So a big part of the video is masked. And then, so the way you use this, right? Once we have our JEPA model trained, right? The way they evaluate it for downstream tasks, right? Because you think, if you look at the architecture, right? Here, what we're doing is just what we're trying to predict in latent space, right? But like, it's not really useful, right? Okay. Hopefully, we do this. We capture some like meaningful representation, some useful representation, right? Does this encoder learns a useful representation? So we're going to take this part, and we're going to use it for some downstream tasks. And so what we do, they actually that works, but they also introduce something called attentive probing. I can't go too deep into this. I still need to take some time to process, but at a high level, the idea is to introduce, it's a bit more complex than the linear probing. And I think they talk about how the weights are, right, because throughout this entire architecture, there's like no place where there's no sort of constraint on normalizing the values, right? Like these values are not bounded, it can just be any value, right? And so perhaps you need to sort of learn how to weigh these. And so attentive probing, number one is, applies this formula, and you apply it's an MLP with an activation function, and there's attention involved. And they use this for the downstream tasks. But yeah, I'm not able to go too deep into how this works. But yeah, I think this is an interesting part that I think the code is also open source. So if you're curious as to how this is implemented, you can take a look in the code base. Okay, all right. So we do all of this, and how are the results? So I was actually looking. So this is from V-JEPA, the first one. Right, so it's like, okay, the argument is predicting the pixels is pretty bad. We should predict in a latent space. So how does this actually translate into downstream performance? So they do see that it does better, but I wouldn't say it's like blows it out of the water. Right? So in these like benchmarks, you see about like it's like point something percent improve, and this one's like, okay, there's a 5% performance improvement for this kinetic 400 data set. But a lot of these other data sets, it's like not that much. Right? So I don't know. There's like an argument that can be made, but so far, when it comes down to looking at the results, I still think it's not that much better. So that's the architecture level. And then V-JEPA 2, which is the paper that we put for today. The main things that I actually talk about is just like how do we scale V-JEPA. So the main things that change is number one, we go from a 2 million video data set that was pre-trained on to 22 million. We also scale up the vision transformer from 300 million to over 1 billion parameters. And then we train for longer. And we also support higher resolution images. And they actually do like a trick where at the beginning you train on lower resolution images, and afterwards you'll train on higher resolution images. So they found that to work better, because training on higher resolution images is just like slower to train. So yeah, this is the pre-training mixture. you can look at what these data sets do. It's like, these are pretty like dynamic data sets, people move. But yeah, V-JEPA takes these three, V-JEPA 2 has these three, but it also has this very huge YouTube data set, and then they also have ImageNet. These are some results. I think here what was interesting is that the video, if you look at the image tasks versus the V-JEPA, the image tasks, it does actually worse. But I think like one reason is in the V-JEPA, they didn't train it on ImageNet, so there's not as much diversity in the videos. So that's why perhaps it did worse. I don't think I saw a table for V-JEPA 2. But yeah, at least like in the image tasks, V-JEPA does worse than the iJEPA, the image-based version. So yeah, and now we're getting to V-JEPA 2. One more thing, yeah, I think V-JEPA 2 talked about how we fine-tune this for robotics. So I think the idea is quite simple. The pre-training is the same, we understand it, but when we fine-tune it, what we're going to do is we're going to introduce the robot actions and poses into the predictor. So the predictor is going to be trained from scratch when you fine-tune it. They use the Droid data set, and that's like I think 62 hours. And yeah, essentially, you create a new predictor from scratch, introduce the robot actions and poses, and your loss is going to be a combination. It's like it's done auto-regressively. The loss looks like this. There's like two losses. One is teacher forcing, which is like, if you're familiar with language modeling and training, it's very similar. And then rollout loss is kind of interesting, where like the issue with like autoregressive models, and even in robotics, right? Like if you get out of distribution, you sort of like don't know how to recover. So this explicitly trains the robots to learn to be correct throughout a rollout. But they use a two-step rollout loss to improve the model's ability to perform autoregressive rollouts at inference time. That's kind of a trick. But yeah, combining these two losses. But if you visualize sort of like how this works, right? The encoder, it doesn't take robot action, right? So you can't just pass like robot tokens, or it only takes in the video, encode this, and then just add tokens for your action and your proprio. And then the predictor learns to predict the next, like the ground truth, next image, and next action, and next state. And then that's the teacher forcing loss, and the rollout loss looks like this. So yeah, I think those are the high level things I want to talk about. And then Krish is going to talk about the results for V-JEPA 2. Yeah. I'll just screen share. Do you have a slides or like you have a Notion? Can you share with me real quick?
Oh yeah, sure.
Because I'm recording on this screen and it'll be easier.
Yeah, I have a pretty different way of just like learning. So I take like constant notes while I'm learning and reading things. So that's why like I do like a Notion kind of thing rather than having like slides. Yeah, I'm happy to share them after if you guys want them. But essentially, like what I'm going to talk about is like how do you evaluate these kind of models, because it's like a very different kind of architecture from something we've ever seen before. And the way they decided to evaluate was like they'll have three models. One, your classic VLA type model, which is like the Octo. And the second is like a video generation model, which has never been done before, of like converting like a video generation model and getting it to essentially work for robots. So those two are like the models that they decided to train like baselines against. And essentially like for baseline 1, for Octo, what they did was they fine-tuned it on the Droid dataset with behavior cloning, which is the same as like, imagine you've taken like a bunch of your data, like imitation learning, and then you've basically tried to train a model to start like cloning and taking actions in the same frame. It's like basically like you try to take a bunch of data, imitate it. And something called hindsight relabeling, where essentially like the idea was any sort of data that is an outcome from the action of the robot is still a correct action. So for example, if the initial idea was like, hey robot, go pick up a can, and it failed to do that, then you'd go back your data set and make that your new label and be like, robot failed to pick up can, kind of thing. So that's how they fine-tune on the Droid data set. And on Cosmos, it's a diffusion model. So all it takes is like input videos, learns over like a vast variety of like videos, and learns how to output videos as well, like which are continuations of like the previous frames. But the way they did this was very interesting, because what they did was they took a bunch of the Droid data set and took the action conditions. And what I mean by that is like they took all the action vectors, and instead of just giving it a bunch of videos so that it understands what to predict next for the video, it tried to like concatenate and add like the action embedding into the frame itself, with the frame embeddings of the video. So what that kind of did was basically force it to behave in a certain way given a set of actions. And so what that kind of like allowed us to do was, imagine if the robot is taking action, we have the joint state, and we have, like, for example, robot move to the right by 10 meters. Then you want to take that into account when you're predicting the next frame as well, because that's how you're seeing how the robot is moving. Because of that, they try to basically use this as like a strong conditional signal and fuse it into the Droid data set and keep Cosmos the same video generation model. Like all it is doing is taking it a bunch of input frames and predicting output frames, but this time the input also includes concatenated action embeddings. And to make sure that the model could actually train, they did like 3 major things. One is like they lowered the learning rate. So what happens is like when you have these massive like video generation models, it's like extremely easy for something called catastrophic forgetting, which is like all the initial learning of the video prior gets lost completely. So like you essentially like erode everything that the model actually initially learned if you have like a steeper learning curve. So you want to have only gradual updates, and that's why you have something, that's why you reduce like the learning rate completely. And then dropout is basically like when you're training these models, you don't want to overfit. And to prevent overfitting, you basically zero out certain frames in your video models from the input frames, or the output frame, or the end frame, or the starting frame. And what they did was like, obviously, like if you have a bunch of Droid dataset videos with actions and you zero out certain spaces, then there's like discontinuity, right? And so you can't risk the robot like making random unseen movements after, or spiking up or spiking down. So that's why like you basically remove dropout completely. And then the third was noise factor, which was basically they didn't see like a strong effect of the action embedding on the training process. So they just upped the noise completely and like forced the model to basically denoise and take the action conditions into account. So those were the 3 ways in which they trained Cosmos. This is the first of its kind, but now you'll start seeing like I think the new model that Unity released like literally yesterday or something uses a similar kind of concept in terms of how it tries to imagine and do like pixel by pixel reconstruction. So what this model actually does is like it's actually just meant to like predict every single new pixel that comes in, but now it does that along with MPC, which is Model Predictive Controller, that was also used for the V-JEPA model. But we'll go into like what MPC exactly is. So those are the different baselines. The setup is simple. You have like a Franca arm with grippers. Then you have, they basically traveled between 2 labs to see how good the generalization was. And what's also interesting is it's all just RGB. There's no input of camera or nothing. And that's actually one of the limitations of this entire process, which is basically, because there was like no exact known camera setting or matrix being used, they had to basically play around with the position of the camera all the time to actually understand what worked, because they would see a massive like reduction in performance if like the base of the robot was not included in the input frame. Because like, for example, if like you tell the robot to move like by 10 meters to the right and the robot frame is not included, then essentially you don't know what the right is. Like the robot, essentially you can't give it good enough actions. And that's why you want to make sure that the robot base frame is included in your RGB images. So they basically played around with like a bunch of different like locations for the camera, and they realized, okay, one of them works, let's just keep it this way. So that was like a massive limitation with how the cameras were calibrated. And when they were testing, they had two different methods for testing against V-JEPA and Cosmos versus Octo. It was blocking or non-blocking, where blocking is basically, it would give it an input frame and the goal frame. And it would basically, like for Cosmos, it would wait 4 minutes for the new predicted frame. And after the prediction was over, it would basically take the action. In the meantime, the robot would not move and no inputs would be given to the model. So essentially like it's blocking because it's not taking constant inputs. Versus non-blocking, it's like you have like this a constant flow of like input frames and the robot's constantly taking actions. So that was the idea behind the operational space control. And then action constraints, essentially you don't want your actions to be, like you don't want your robot to like randomly move from point A to point B, but there's a massive difference between the 2 points. You want them to slowly make gradual changes so that there's no like out of distribution movements. And for that, they had like something called an L1 ball radius. So imagine the XYZ position, and they basically limited the L1 distance, which is just this thing right here. Delta X, delta Y, delta Z is less than 0.075. They limited the movement to be within this constraint, and ball radius is like a ball. And so this was the setup. In terms of how the model predictive controller actually worked is like you sample a bunch of actions and over like a normal distribution, and you feed like each candidate action along with like the input frames into any of your models like Cosmos or V-JEPA, because Octo on the other hand is like a VLA. So all it takes is like the input frame and predicts the action. But for Cosmos and V-JEPA, you essentially take the input frame and you have to give it a bunch of different candidate actions. And then basically you check, okay, this is the imagined frame, is it moving closer to the goal frame? If it is, you look at the loss in terms of the pixels, and if it is moving closer and closer, you essentially use something called the cross entropy method, which is like, which of these actions allows me to make the least amount of movement to get to my goal frame from my current frame. And so you do that. It's like giving a robot a basic like imagination. So like you're simulating in your head as to these are the new frames that are going to get created. And you check across all of them. If your goal is being met by one frame, then you basically keep moving by, and at each step, you essentially keep sampling different actions, and you keep checking for the easiest way to get to your goal. So that's how like the MPC controller exactly worked. Yeah, and so the reason why Cosmos was like was blocking was because it would take 4 minutes to inference. So basically, you had to wait a long time, primarily because you would have to essentially do a pixel-wise reconstruction for each time the frame basically got created. Versus in V-JEPA, as Steven was saying, we do everything in the latent space. So the difference is 4 minutes versus 16 seconds. And because you're working only in the latent space, it's much faster to inference and you know exactly what's going on. So that's like the reason why Cosmos seems like a cool method of doing things, but is just not scalable. And then something that I think Steven was like, I'll just like touch upon it, but like essentially like you have something called the energy landscape, and this is the energy landscape. And some of the images that you saw before were like, if you remember, the regularization was a non-regularization bit. This plays on the same bit essentially, and essentially an energy landscape is like how far off the actions predictions are. Now imagine you have a bunch of different frames. You don't want to be able to predict things like one-to-one. You don't want things to be flat in the latent space as well, because then you can't differentiate. To allow for better differentiation, you essentially want to make sure that you regularize your entire frames, set of frames, and then you essentially look at the energy landscape there and try to differentiate over it to have the best optimized route to get to your goal point. Over here, the point at the very minimum was exactly your goal point. So you were always trying to differentiate from your existing frames, and everything that's far away from the minimum is basically out of distribution movements. So that's how the energy landscape works. In terms of tasks, they tried like single goal reaching. So they have a start frame and a goal frame, and essentially at each step, you try to get closer and closer to the goal frame. So this is all the model was trying to predict, either in the latent space or in the pixel-wise reconstruction space. And then you essentially looked at delta x, delta y, delta z. And almost generally, it was like you would try to reduce the energy, you would try to optimize on the energy landscape and reduce the loss. And so you would essentially keep going closer and closer to your goal frame. And that's what they were able to achieve. Then they also tried a bunch of manipulation tasks. One thing very interesting was like for long-term like pick and place kind of tasks, they had to actually give it like sub goals. So at each movement, what they did was like, let's say it was this step one was grasping the object. So they would give the goal frame as the grasped image of the object. And then at each step, instead of it being one simple task, they would basically change the goal frame once the task was achieved. So object grasp, image change to the next task. And then once the next task is achieved, image is changed to the object placed step. So at each step, you would basically keep checking. So it was not like a long horizon task, but it was just a bunch of different tasks, one after the other. Yeah, humans in the loop, essentially. And so it's like, this was one of the biggest caveats with the paper, where it's like they weren't able to achieve long horizon tasks, but they were definitely able to like take it from each sub-step and continue it. So that's sort of like the idea with the pick and place task that they evaluated on. And you'll see how like the model actually performed extremely well for pretty much all the tasks. And it's all zero shot, runs on those Panda ARM robots, which is the Droid data set anyways. So out of the box, you just get really good performance. I don't quite care for the stats because these stats are not like statistically super relevant, but like, yeah, it's like, you know, there's always an asterisk, and so like evals in robotics are like not the best right now, but that's all the idea here. And then yeah, so one of the three limitations were long horizon tasks because they had to break it down into subtasks, sensitivity to camera positioning. And then one thing that they realized they wanted to do was like, right now they were giving it goals for the images, and this is where you want to go, but you want to be able to steer the model a little bit better, and for that you need something like language. So the next steps and next iterations for the authors is like, can we go from like image goals to like just language goals and be able to see the robot perform. The next steps are like, basically if these action condition models are like so good, they can tell the robot what to do, wouldn't the latent space also include like a bunch of more information? And so like, can we go beyond robotics then? So what did they test for? They tested for motion understanding, appearance understanding, anticipation, and reasoning. That they tested on was like, let's say you have like your context frames, which are the input frames given to the model, and then the model makes a few predictions, and then after a second you try to see if it reached that prediction or not. And if true, then we know that it can anticipate the next actions pretty well. So that was sort of the idea behind how they tried to probe for it. And I think Steven was talking about linear probing and attentive probing. And that's basically what they did. The question was like, okay, how do we test for it without actually having to retrain the entire model? You don't want to change around the architecture. You've already trained this model on a bunch of things in the latent space. What's next, right? So you train this small little probe network based on the task and the evaluation metrics. And essentially you try to look for these 4 different types of understandings from the model itself. And well, spoiler alert, it does pretty much state of the art in literally everything. which is great news for us because self-supervision works then, and data scaling works, and we're going to solve robotics. But essentially what they did was like, the general architecture was you have a frozen encoder, which is your base V-JEPA model, and then you have this learned probe, which could be linear or attentive. And then you have some sort of pre-processing step for the input frames. And then you take the encoder outputs for those frames. And then based on the type of like task it's expected to do, you have some sort of a probe. The general architecture for the probe was you have a transformer block with self-attention over the same set of encoder values, and you have 3 of those. And then final layer is like you have a cross-attention block where basically you query and do cross-attention across the other 3 layers of the encoder outputs. And then you have a pooled representation. And then finally you have like a classification head. And the idea was like for motion, you look for example, this was the motion understanding data set that they check for, where all of these images are basically like a video of the task that it's supposed to perform. And basically you encode and expect the logits to match directly with the output from the classification head. And that's how they tested whether things were closer or far away from the understanding. For appearance understanding, they had this kind of a layout where it's like you have a bunch of original frames, and then you have a bunch of like output frames, and you want to understand whether it is able to predict whether the last frame is feeding goat. So that's just like what's the current appearance of the frame itself. And then you have this anticipation benchmark, which is it has transparency. So in anticipation, you essentially have like observed and future frames, and you're basically anticipating whether the next action is going to be X or Z or Y. And it did a pretty good job at that. And then finally you have some video question answering. So this is interesting because the code actually never has any information on how they do the alignment over here. But like the only thing that the authors end up leaving us with is that look into how Lava does video and text fusion. So if you guys want to like check out how the attention mechanism works for Lava, you will understand how they were able to basically align the existing model with text as well. So, and then they did like reasoning over it. Always, yeah. Correct. Yeah. So which is why it's like very interesting how they were able to align them together. It is still a question in my head because I haven't looked at the Lava code yet. But yeah, if you guys are interested, you guys should definitely check out the Lava fusion methods for how they were able to combine 2 different things together. Because in Lava as well, you have 2 different pre-trained models, and they do some fusion step to allow for the 2 different attention mechanisms to line up at the very end. So yeah, it's kind of interesting pretty much there. And yeah, so pretty much better everything. For exact figures, you can just check the paper. Again, evals don't matter. And yeah, when evaluating, they also like made sure like they use the same relative probes with existing state-of-the-art encoders just to measure the encoder strength rather than also like check for the probe strength. Yeah, so in general, like I think for discussion, there were like a couple questions that I thought about, or just like along the lines of like, can models trained on video truly anticipate what's going to happen next? Or do we need more models like simulation based where it can go ahead and explore like a bunch of different outcomes and then have a better understanding of how objects interact? Or do we go ahead and scale up like all potential outcomes from video generation and use that as a means for us to train most of our models? Like, do we really need inherent like reasoning is like the question that I tend to pose, if you guys have thoughts on that. But
let me ask some, I guess I have a question. Just I didn't fully understand that when you pass in the goal image, where is that fed? Is that fed through the encoder?
correct, yes. So both are fed into the encoder, and like essentially you're trying to minimize the loss between the encoder frame. So you have
I mean, at inference time, do you pass it over?
no, at inference time you don't. Yeah, only in the training phase you pass both, and then you predict the next frame, and then you try to minimize for the loss between the goal frame and the predicted frame. Any questions? Any thoughts on this?
We're talking about how you need you're going to like decompose the tasks. Is that done for both of the models, like the context?
Yes. Yeah. So like baselines, like because like both are done on the same thought process, which is like video generation and then MPC. One does video construction, the other one does latent representation. Yeah, do you guys have thoughts on like reasoning?
Yeah. I think we can have a general discussion after. Let's first, if anyone has specific questions on the paper, and then we talk about some of these ideas. I have some thoughts in general that I would like to share as well. Does anyone have any like implementation or like details of the paper that they didn't understand?
What is
Lava?
Lava?
Lava is basically like one of the first attempts by Meta, or probably one of the few models that were actually good before everything else became really good, which is basically like the text, like video model, essentially. Like you can, like how Gemini does video understanding, Lava did that.
Oh, okay. No one else has questions. I mean, I can share some thoughts. I think, well, number one, my thought is like, yeah, a lot of times one feature that this model is missing is like the being able to condition at inference time on different things. So either conditioning on language, for example, right? So I mean, you can imagine if I put like an apple and a banana in front of you, and sometimes I wanted to pick up the banana, sometimes I wanted to pick up the apple, right? You sort of need some way to condition your model to take out these different trajectories. And it seems like they have no way of doing that, right? That's number one. So a lot of times, if you look at the other robot foundation models, like they have conditioning on language. First thing. Number two, I guess like more generally, Krish, I'd like to hear your thoughts on, I guess you talked a little bit about, yeah, generative models and like, let's say, like for example, diffusion models and leveraging more of like the fact that they can capture multimodal distributions, things like that. Do you see if they have any place in world models?
Like capturing what specifically?
Like if you use the diffusion model here, or like diffusion models in general, as opposed to this sort of like, I guess I haven't seen too many diffusion models, and I guess the idea why is like do you think, because if you look at the video generation model, right, a lot of people just use diffusion models. Like diffusion models is just you start from noise, generate an image, right? Whereas here what we're doing is more like the in-painting style, where you're trying to like predict within your patches, right? So you're not like creating a new image from scratch.
Yeah.
So I guess that was a question when I first read it. I was like, where do the diffusion models fit into the picture? But then for me, it made sense that that's kind of why they don't use diffusion models. Yeah.
Also, like just like pure diffusion models, when you're doing some sort of like pixel reconstruction, they're just like slow.
Yeah.
Right?
And even here, you said it took 16 seconds, like that.
4 minutes for the Cosmos model.
Right. Like that's not realistic to use online, right?
Yeah.
In the real world.
It's not fast enough.
Yeah.
I think different architectures like behavior transformers have like 5-second interface.
I'm really surprised it's 16.
Yeah.
That's a long time.
That is a lot. It's 3x slower than the standard average model.
Yeah.
Which is probably, if boosted, could be much faster.
Yeah.
I think it's like 2 to 4 frames when predicting. So it's like pretty slow in that regard as well.
Why is it so slow?
Just the architecture.
What makes the architecture slow?
Good question. I would assume like
It's not like a RNN or like there's. I mean, if you look at the Pi model or like the other foundation models, they don't take that long.
for
right?
diffusion policy.
Like any of the robot foundation models that we covered last week.
Yeah.
I mean, they do action chunking, right? But like, even like for one prediction, it doesn't take it like almost a second. Like I don't know how. Maybe they didn't optimize the model for inference, and
I mean, there's no mention of that. But like, you're also looking at like you're trying to like create batches of each of the images, right? And you're putting a bunch of like, which is kind of similar for any of the other models.
yeah,
But over here, you're also doing MPC,
yeah, okay.
right? So MPC is much slower than.
I think, yeah.
Just like
I guess
you
that's where
have
the
to-
overhead is in.
'Cause,
I guess
like,
they
you're
didn't
predicting,
share-
like the next few set of rollouts.
Yeah.
And then you're basically looking at the best one and then taking the action.
Yeah, okay. That's probably why it's.
Yeah.
All right, cool. All right, thank you all. For next week, does anyone want to volunteer to present?
What paper?
Do I choose a paper for you and then you can present it?
I mean, go for it. I'm not volunteering right now. I was want to give some
Yeah, there's a few more topics. I think whatever is, if there's something interesting, like a paper or like a topic that you want to learn more about, feel free to run it by us and then we'll tell you. And then I think, yeah, as long as we can sort of like give a literature overview of related papers. Yeah, you want to say? You have a paper for next week?
I need to first understand what you said today.
Okay. Sounds
Wait,
good.
like just like informal, like quick feedback, like was like what is like not working, what is working?
Yeah, I think, well, last week we got feedback that you want more interaction a bit. So I think, yeah, I think we didn't do that today still. Perhaps we should like pause more and ask questions in between. Yeah.
The idea with interaction is also like the expectations that everyone's read the paper.
Yeah, I think it's difficult. I mean, by raise of hands, who has like read a lot of the paper today? Okay, so if you read like a lot of the paper, then all of this is like basically a review, right? Or were there still?
I remember when it came out, so it was kind of reviewed, but I knew the
The
core ideas.
core ideas, right? And yeah, I think that's where like the annotation comes in, and then we can have discussion. Today we didn't have any annotations to discuss, so I think if we go to an annotation, I think maybe we should time ourselves and make sure the presentation takes at most like 10 to 20 minutes,
Okay.
and then spend more of the time discussing. I think that'll be good.
I mean, I think also the ways that you're presenting, like during the whole thing right now, is that you come in and then you talk about like related papers and stuff like that. I mean, which is good. I think it's giving context, right? But like,
Yeah.
you yourself as a presenter are approaching this more as a teaching thing rather than a discussion thing.
Right. Yeah.
So like, I think like that's like, well, because a lot of it, I read the paper, but like a lot of stuff that you mentioned at the beginning were pulled from other papers, and I'm like, if you're gonna mention those papers as well, then might as well link those as well, right? So I can, because the whole point is to be discussing them.
You mean I should link them in the?
Like for example, like I only had time to read the V-JEPA. I didn't read V-JEPA 2.
Right.
But I don't think you linked I-JEPA unless you did, and I just didn't see it. Did you link I-JEPA over there?
Yeah, I guess I didn't link the papers before. Yeah, if I didn't, I'll make sure. Yeah. I mean, it was also something I just found out as I read more of the paper.
Or like, I guess maybe like an itinerary on what we want to discuss beforehand. Like, I think that might be helpful as well. Like, for example, so the paper, like, all these papers like go over like the basic like vision transformer, the transformer attention portion, right? But
Right.
like reading that's like, you know, kind of useless because everybody like has basic knowledge, I feel like.
Yeah.
So like, why not like, what makes this paper unique? Like, what makes this paper worth talking about? and then maybe it's the attention like pooling part, like not the exact name of it.
Attentive probing.
Attentive probing, yeah, sorry.
Right.
Maybe that was the part that made this paper like interesting, right?
Yeah.
So maybe like have some questions like related to that, like why attention probing and why like this not that, and like maybe like that would be more interesting.
Yeah, I think I want to do more of that as well.
Yeah.
But I think somewhere down the line, I dropped the ball there.
I think because you ask questions at the end.
Yeah.
I think maybe like
Yeah, I think let's try to, and for future speakers as well, let's really be intentional about making it more interactive. And
actually, I volunteer. I'll do a paper because I don't want to be just telling you like, oh, do this, do that. But I think if I want, I'll do one, and I'll try my best to make it the way that I think I would like it.
yeah, I think
Yeah,
that'd be
that's
good.
also that's a great setting point, right?
Yeah, I think it'll be good, and we can also see what works, what doesn't work, because when you're presenting, it's
I have a question.
Yeah.
Are we only focusing on models like models for robots, or are we also going to look into papers maybe regarding hardware or other parts of robotics? Because I've been trying to read into DAXA robotics, if anyone has heard of it. They've got like a weird robotic hand, and I thought it was really, really cool, but it's, I feel like it'd be a lot more challenging for them to implement software as well as models for that specific hand.
So they are doing a pretty good job in terms of like how they do simulations.
Yeah.
But obviously like they don't open source any of this information, right? So in that case, like there are no better like things to look at. But we can, I guess like we could
DAXA robotics.
Discuss how they could potentially.
we could do sim to real stuff as well, if that's interesting, because then that would go into hardware as well. Yeah, maybe like the next paper could be something related to sim to real.
Do you have a paper in mind? You want to talk about hands? I mean, there's some. I mean, I'm thinking of like the UMI series. So like, there's some hand papers as well. Like Sharon's.
I think the human egocentric line of work, or like any of the. Like I know there's a new paper that just came out where they trained completely in simulation, and they were able to do zero shot on the robot, which is like incredible.
There's like some teleop. Oh, there's this. Whole body teleop.
Oh yeah, this one. Yeah.
I mean, that's not as much hardware. It's like. I mean, it's not even Centurial, but it's teleop for the whole body. I don't think it's too.
Gene control.
Yeah. Also, I guess like because we have an alpha Kive now.
Search gene control.
Huh? This one?
No. It's a new paper, so I don't even know if they have a preview or not.
Or how much is fine?
I have it on Twitter. That's the one.
Oh, the is this by Unity or?
It's by Giant Robotics. Yeah, maybe we could do something like this, but this won't go completely deep into like hardware, but it'll talk about how the retargeting works.
Right. I don't know. Yeah. I mean, I would. For example, for this paper, like, I think you need context on the history of like.
How sim really works.
Yes, like a lot of the work was like by like back in the days when they first like motion retargeting, the history of like how motion retargeting works, and it was like sim to sim, taking mocap data and then training it, and then like I feel like you get to here. I guess that's my style of like teaching how like things
No, this
work.
makes sense. I think this is jumping straight into like what is now possible versus what used to be the case.
Because I think to discuss, what are the like, innovations of this paper, you sort of need context on like what has been done, right? And like that requires everyone to be like at the same level. And I guess that's why I try to like first give everyone a context. So even for myself, a lot of these papers, like even representation learning, I didn't know that much, and like I need to give myself context. And if like I need to give myself context, then like other people also probably need that context. If you just say like, this is new. Like maybe it's not enough. Like it's just too much. But maybe we can just directly jump into that.
I
Yeah.
have a discussion question for you.
Yeah.
What do you think of these types of role model based approaches versus something more like imitation learning based, like Pi0, like as far as
I mean, you could argue Pi0 is also a role model, right? In the sense that it learns some representation. But if you look at Pi0, right, like what it uses is a VLM, right? But the VLM is literally, it was like, it's mostly LLM, and then you have clip, right? And I don't think clip has that good of like spatial understanding. Whereas this role model, like the way it's trained is you mask stuff, right? And you like predict these.
Exactly. Yeah.
And so I think
some combination of like self-supervised learning for the backbone mixed with some sort of like reasoning stuff with already existing action.
Which maybe Pi 0.5, I didn't fully read it, but does it do that? I mean, it had, like, you predict multiple things, right? So it combines, like, I assume you could, like, do masking, and you just add, like, multiple objectives to it, right? And then it would help it generalize. Yeah. Okay, anyways, thank you guys for listening today, and we can feel free to stay around and finish the pizzas, and we will see you next week if Ayush will be presenting, and we'll give him a paper. And if anyone else wants to volunteer, you can message me or Krish, let us know, and then we will gladly let you host the paper. Cool, thank you.